Modern AI models have scaled to a size where they no longer fit on a single machine, forced into distributed inference networks spanning physical geography. To function, these distributed models must constantly pass data between layers using a central pipeline known as the transformer residual stream. In its uncompressed state, this baseline stream has a standard data dimension, which we call D. Moving the full dimension D across hundreds of miles of fiber optic cable introduces severe latency. The physical network connection is simply too narrow to handle the volume. Engineers attempt to bypass this by applying linear compression, shrinking the data stream to a smaller dimension, or rink, called K. The constraints governing this transition are strict. They are formally captured in the Lean4 proof file labeled compression uncertainty. Squeezing the data pipe is an obvious fix for network limits, but doing so forces an unavoidable collapse of the actual information inside the stream. We start by measuring a model's baseline fidelity. When the system uses the full dimension, where K equals D, the accuracy is perfectly maintained at a fidelity score of 1. Testing shows that applying any deterministic linear compression, where K is less than D, forces that fidelity score strictly below 1. This chart compares the quantitative values of the full dimension D against the compressed rank K. The fidelity score shown here represents the fraction of next token argmaxes, the actual words the model chooses, that survive the compression. We can see this in a specific empirical test using the Quen 2.5-0.5b model, which starts with a baseline dimension D of 896. Researchers compress this stream, dropping the rank K to 700. This is only a 22% truncation of the data. In response to that minor truncation, the preserved argmax fidelity plummeted to 0.40. The 60% loss stems from a rigid information theoretic barrier at the residual sum, rather than simple precision rounding. Simple linear compression permanently degrades the model's accuracy. The original identity of the output is destroyed. The compression uncertainty principle dictates that trading bandwidth for precision guarantees a loss of identity. We have to use a different structural approach. We bypass the rank K barrier using an architectural escape hatch known as the top K verify protocol. This setup strictly divides the inference process across a boundary into two discrete roles, a sender and a receiver. The sender computes a draft of the next step using the heavily compressed lower rank K stream. Instead of transmitting a single compromised answer, the sender transmits a top K list of candidate tokens across the boundary. The receiver catches this drafted list of candidates. Crucially, the receiver then runs a verify check. It computes the true baseline argmax from scratch using the full-width data stream. If the receiver's true token appears anywhere in the sender's candidate list, the draft is accepted. If the true token is missing, the draft is rejected, and the receiver outputs its own newly calculated token instead. Because the verifier acts as an absolute gatekeeper against the true baseline, the final output fidelity is mathematically restored to exactly 1. The structural guarantee of the system is formalized in the verify preserves identity proof. It circumvents the compression limit by introducing a third resource into the equation, verify side compute. To measure the actual efficiency of this system, we calculate the effective bandwidth. This equation calculates the first half of the composition, the drafted bandwidth multiplied by the probability of a top K hit. The second half adds the full baseline bandwidth, which is paid every time there is a rollback. The actual performance of the system is deterministic, governed entirely by this exact composition of hit rates and bandwidths. Perfect identity is achievable, but it is paid for in computational overhead, forcing us to balance an asymmetric ledger. The true cost of this overhead is captured in the total compute exceeds baseline theorem. While the protocol saves network bandwidth, it drastically inflates total computational energy. This chart compares the total computational cost of the verify system against a standard baseline model. The combined compute of the sender and receiver will always be strictly greater than running the baseline model alone. The sender's cost is relatively low, paying only a fraction of the baseline compute, determined by the ratio of K to D. But the receiver pays the full baseline compute every single time it runs the verify check. This imbalance is defined by the ledger is asymmetric theorem. The two nodes operate under entirely different economic costs. We have successfully traded the sender's compute and the pipeline's bandwidth for a massive brute force increase in the receiver's workload. If this protocol demands strictly more computational power, why is it valuable? On a single host machine, this compression protocol fails completely because local computational power is the primary limit. The massive compute penalty required by the receiver node bogs down a single processor, erasing any theoretical speedup. But in a distributed inference system, physical distance creates severe transmission bottlenecks. In these networks, the microchips possess abundant processing power, but the data pipeline connecting them is starved for bandwidth. The Verify protocol exploits this exact reality. It offloads the network bottleneck onto the abundant local computing power. The compression uncertainty principle proves you cannot defy information limits, but by utilizing formal mathematics and asymmetric verification, you can engineer around them to scale distributed inference across massive physical distances.